Welcome, ladies and gentlemen. What I'd like to do in the next 10 minutes or so is to give you an overview of where we stand right now with 5G standardization and how the 5G standardization roadmap looks for the coming years. But before I start, just a few words about the major use case families for 5G. We know that mobile broadband is that first use case which is gaining a lot of traction right now. It is the main priority for many operators. We understand mobile broadband, we know how to sell mobile broadband. So it's an important first step, and that was included in the first phase of 5G standards. But in the second phase, which is now complete, we had the availability of ultra reliable low latency communications and massive machine type communications. And it's really the combination of all three of these use case families that provides the compelling opportunity for 5G going forwards. Many industrial sectors are looking to use 5G to meet their needs, and they will in most cases make use of all three of those use case families. In terms of where we are though with 5G deployment right now, taking my data from the Global Mobile Suppliers Association, we know that 92 commercial networks were launched as of August 2020, and they were launched in 38 countries. We know there are 86 vendors currently producing 5G equipment. We know that 50 countries are planning to auction 5G spectrum by the end of 2022, but we know that 47 countries have already assigned 5G spectrum. So with this rather large deployment, although it's in its infancy, what do we expect will come next? Well, first of all, about spectrum. Yes, many spectrum bands have been auctioned, but 3GPP has also extended the capability of the 5G system to work in unlicensed spectrum. Until recently, the use of that unlicensed spectrum was as an addition to the licensed holding you would have, so the spectrum was aggregated using 5G as the anchor. What more recently has taken place is that the standards allow standalone operation of 5G in unlicensed spectrum, so there is no need to aggregate or anchor with 5G. Now this adds a lot of flexibility for deployment scenarios. In areas where maybe that unlicensed spectrum is underutilized, it enables 5G operators to make use of that spectrum. It gives a lot of flexibility in industrial scenarios, but of course in doing so, we have to be careful that we don't cause undue harm to other occupants that may well be in those bands. So the standardization philosophy in including this capability has been that the 5G component should act as a good neighbor and ensure that there is fair and equitable use of these bands. Another important change, I believe, is the inclusion of non-terrestrial components within 5G standards. In previous generations, either there has been no satellite component at all, or there has been a non-integrated add-on component, which has not really been very efficient. What 3GPP has done is exhaustively study how we can include non-terrestrial networks within our system design so that you can move seamlessly between terrestrial and non-terrestrial coverage. If we manage to achieve that, of course, then this offers an awful lot of opportunity for covering sparsely populated geographical areas, for example, or areas that are not covered by land-based systems, here I mean oceans, and also for providing alleviation in terms of public safety disaster scenario systems. It's quite clear that if you achieve a good global non-terrestrial coverage platform, then there are many, many opportunities as to how you can actually exploit that platform. Now, as I said, the studies have been largely complete. The normative work will now start in release 17. And of particular interest here is to see how narrowband IoT can be carried by a 5G carrier over satellite. And this will be the main focus then for release 17 moving forward. If we look at some of the industrial sectors we're trying to serve, it's clear that for many of them, the use of a purely public mobile network operator as the service provider is not really the most efficient scenario. There are cases where you have campuses or you have industrial plants where maybe it's more appropriate and more attractive to have a non-public offering there, where maybe the factory has its own service provider who manages and operates the network within that campus. Or it might be that perhaps the industrial region wants to lease a slice from a public network operator, but manage and operate that slice themselves. So what 3GPP has done is look at all three of those scenarios and standardize the use case where you use a public mobile network operator as your provider. You have a completely non-public network approach to servicing your industrial campus, or indeed you have some hybrid version. And I've given you the reference here on the screen should you wish to go away and learn more about that. Also, for many of the industrial applications, we see this demand for much more accurate positioning capability. Until now, the positioning capability in our systems has largely been driven by regulatory requirements, and we've aimed to meet the minimum requirements for geographical areas in terms of accuracy. But many of the industrial use cases require accuracy much greater than that stipulated in regulatory requirements. And here we're looking at accuracies down to below 1 meter, so maybe a few centimeters. That there are industrial applications which are demanding that. So a lot of work has been done in Release 16 to understand how we can address that demand. Not only does the positioning need to be very accurate, it also needs to be provided very quickly. There are applications where the availability of positioning needs to be updated very rapidly, especially if we're looking at devices that are moving at speed. So here I've given you the reference again on the screen. If you want to go away and read more about this, it's a very interesting study as to how we can get down to this centimeter accuracy of positioning, which will now be standardized within Release 17. We also see a move towards massive IoT. We know that IoT is getting traction. It's starting to build in many parts of the world. But at some point, we will approach the massive capacity for IoT. And here we're looking at something like 1 million devices per square kilometer. And there's an illustration on the screen here of a container ship where the containers on that ship are being tracked and aggregated by a gateway on the bridge so that the owners of the contents of those containers can always know where that container is throughout the world. Now, it's a relatively simple use case, but the combination of these many devices together with the clusters of devices that you see in this illustration, you soon then approach this context of massive capacity. And we know that our systems today cope very well with the sort of volumes we have today, but we know that changes will need to be made if we're going to cater for this massive capability of the future. And of course, very simple things like devices which have nothing to say should say nothing. If we give the example of, for example, electricity meters, maybe electricity meters in a city when providing their daily update, if they were all to provide those updates at the same point in time, they would cause congestion and disruption to our networks. So we need to randomly spread the transmit time of these massive devices. On the other hand, we may need to address all of these devices at some point in time in the context of device grouping. And again, if we want to address all of the electricity meters in a city, we have to then consider those electricity meters to be part of a group. And this then stresses our numbering and addressing capabilities. And we see here where IPv6 is very likely to succeed the E164 current numbering capability. Of course, all of the use cases I've given so far are dependent on having total trust in the security of the system. And we know that if we're addressing, say, health or banking, automotive or industrial applications, it's imperative that we have total trust in the security of our networks. Now, 5G is secure by design, it's inherently secure. What we've more recently done in 3GPP though is have a look at the industrial needs that are perhaps more specific to certain categories or certain families of devices. And the example I've given here is for industrial IoT, where a study has been undertaken in release 16 to understand more about the dedicated security mechanisms we need to address these markets. And as we go forward and address new markets, it's inevitable that we will continue to work then on upgrading our security capability so that the end consumers of our system continue to have total trust in the service we are offering. Time for some conclusions then. Mobile broadband for sure is the use case completed within release 15 and 16. It's the basis for the networks which have been employed to date. If we look at 3GPP releases 17 and 18, they will focus on the industrial expansion of 5G. We see many industry sectors demand high availability, high reliability, low latency and secure communications, which 5G inherently supports. We can note that 5G is designed for use in both licensed and unlicensed spectrum and for use in both public and non-public network configurations. We can note that 5G is designed to provide coverage using both terrestrial and non-terrestrial technologies, and it's designed to cater for eventual massive network capacity. And I believe the industrial expansion of 5G deployments will be enabled by these key attributes. Thank you very much.